Hey, good morning. Hope everyone's doing well. We are going to take a look at heating and cooling curves. Okay, this has to do with phase changes and heat transfer. Okay, I'm going to share my screen. All righty then, let's do this. Have your calculator ready, guys. Turn it on. Be present. All right. There we go. Like I already named it. Heating and cooling curves. This is to do with phase changes. All right. And we will need to talk about some constants. I have them written down here in case I forget them, but I'm going to rewrite them again. All right. We're going to talk about C, the specific heat of water in its solid form. And I believe that is what, 2.05. Yep. Joules per gram degree Celsius. We'll talk about the specific heat of water in its liquid form, which is 4.184 joules per gram degree Celsius. And we'll talk about the specific heat of water in its gaseous or vapor form, and that is 2.08. That's right. Very similar to the solid, joules per gram degree Celsius. We also have a new term. It's going to be called the enthalpy or delta. Triangle means delta. H fusion. All right. I guess I'll need to go into that. That is 6.02 kilojoules per mole. And that is for water, particular to water. We will call this enthalpy of fusion, or you could call it delta H. If the triangle means delta, delta means change in H means heat, delta H fusion. Okay, so this here kind of means change in energy to go from solid to liquid or liquid to solid. All right. Now, it's very important that you realize that when we talk about these phase changes, all right, if we are going from a solid to a liquid, right, we must add energy. Heat must be added. We have a positive Q, we have a positive delta H, and we are endothermic, right? That simply means we are adding heat. All right. That would also be the same if we were going from a liquid to a gas. We would have to add heat. It would also be the same if we were going from a solid to a gas. All of these processes are endothermic. They have positive Q values, positive delta H values. Excuse me. In addition to that, we know we call this what? Melting, evaporating. And when we go to from a solid to a gas, that is sublimation. Okay. You would see your dry ice, right? Solid carbon dioxide goes directly to a gas and it never turns into a liquid, all right? That's true. Sorry. Okay. We also have this particular, though, this is our fusion, right? If we are adding heat, because it goes from the solid to the liquid. And fusion entails solid to liquid. All right, you need to know that. Solid to liquid. Well, we already wrote it. We wrote it right here, right? So these go together. Fusion does not pertain to liquid to gas, solid to gas, right? Fusion pertains to the solid, liquid, liquid, solid. We've also got the delta H VAP, all right? So let me write that down. Delta H VAP, it stands for the heat, oops, I spelled that wrong. Heat of vaporization. They'll also call it delta H, delta for the T, again, T means change, delta H, vaporization, or delta H VAP, right? Vaporization. And vaporization deals with the gas to the liquid, or we could be in reverse and be going from the liquid to the gas. And it would have to do with the change in energy, right? Change in energy for the gas to liquid process or the liquid to gas process. Okay. Now, if we are turning a gas into a liquid, you know that we must remove heat. So heat is a product. Heat is removed. All right. We got to cool it down. We've got to remove the heat. That is an exothermic process. We have a negative Q. We have a negative delta H. It is exothermic. And what that means is heat is being removed, right? I wrote that already from the system. All right. So the system is losing kinetic energy, right? Here we would say that the system is losing kinetic energy. Up here we would say that the system is gaining. Actually, that's not necessarily true. The type of energy it's gaining depends on the, I don't want to say kinetic energy. I'm not even going to write that because that might end up being confusing at some point. Okay, so I'm going to do that. Okay, I'll bring that back up later. All right, so we've got several terms here. We've got the specific heat of water in a solid state, the specific heat of water in its liquid state, the specific heat of water or H2O in its gaseous phase. We have the heat of fusion for water. That's how much heat must be added or removed to go in between the solid and liquid state of water. We've got the heat of vaporization for water. That is 40.2 kilojoules per mole, okay? The heat of vaporization is the energy that must be added or removed to go between the gaseous and the liquid state, okay? That is an exothermic process, right? If you go from the gas to the liquid, right? Gas to liquid is exothermic. What else is? Anytime you condense, so the liquid to the solid is exothermic, and the gas to the solid is exothermic. All of these, we must remove heat. These are your phase changes, right? This is condensation. You know this. Liquid to solid is freezing. And then the gas to the solid is called deposition. All right, there's something called a phase graph, not a heating curve, and it typically looks something like this. All right, And what you have right here is always the solid, the liquid, and the gas. This is your pressure. This is your temperature. All right? Standard, normal pressure equals 760 atmospheres or 1.0, no, I just did that wrong. 760 mmHg, millimeters mercury, or 1.00 atmospheres. This is your pressure, all right? So right here is my solid to liquid line. Right here is my liquid to gas line. And right here is my solid to gas line. So if my pressure, let me move this a little bit out of my way, right? If my pressure were normal, 1, solid to liquid, and this was for water, right? Then let's make our pressure standard, 760 mmHg or 1.00 atm. At that standard pressure, normal pressure, my solid to liquid line would fall at what temperature? Remember, this is water. Well, that solid to liquid is either freezing, liquid to solid, or melting, solid to liquid. That will occur at the same temperature. The difference is, are we adding heat or are we removing heat? So that will occur at 0 degrees Celsius because this is for water. And then we would see the same thing if we would go once again to our normal everyday pressure and read over to our liquid, let's make that longer, to gas line, right? And remember, liquid to gas is boiling or condensation, right? Depending on if you're adding or removing the heat. And we could read that down to the temperature. And if this was water, we would see that that would be occurring at 100 degrees Celsius. All right, once again, we know those temperatures because we are discussing water. All right. Water also has a negative slope at the solid liquid line. And that is because the solid is less dense than the liquid. That is usually not the case. Okay, that's why. And that is why ice floats, right? Ice, actually, water expands when it freezes, where most other things condense when they freeze. But water expands when it freezes due to the hydrogen bonding that we've discussed. All right. So this is not a heating cooling curve. This is kind of like a graph, and we can determine freezing points, right? This is a boiling point or condensation point. And this is a freezing point or a melting point, right? If we wanted to know at what temperature, when would this substance sublime, we would need to look at this right here and figure out at what temp and pressure would that happen, because it's not going to happen. You've got to really lower that pressure. This is not to scale. Okay, cool. All right. If I was to draw one of these for another substance that was not liquid water, right? My temperature's here, my pressure's here, I would see this, okay? And what I would have here is a positive slope. And therefore, this is not a phase graph for water, right? It could be for many other substances, But due to the positive, this is my solid, this is my liquid, this is my gas. Due to the positive slope right here, I know not water. So I'm not going to tell you what this is, but we're going to assume it is not water. Okay, because that positive is, that slope is, once again, positive. Over here, we would have a negative slope. Another point, another thing to identify is this right here is called my triple point, right? And what that means is that at this temperature, whatever it might be, and this pressure, whatever it might be, all three phases, right? The solid, the liquid, and the gas exist in equilibrium with each other, okay? So all are present. And it's hard to think about. Okay. And then what we have lastly would be the end of this line here. And this is called the critical point. So that line does not extend, it ends. And beyond this temp, right, at this critical point, beyond whatever that temp may be, the gas phase is only present, right? So no matter how much pressure you push down on beyond this point, the gas phase is the only phase possible. The temperature is just too high for that. Okay? So we actually, guys, did not get into heating and cooling curves. We got into phase changes and graphs. And what I will do is I will end it here and make another video about heating and cooling curves so that we could keep it in small little pieces, okay? Oops, let's see if there's anything else I would want to say there. Okay, I do want to clarify that if you were asked for the normal boiling point, then your pressure needs to be normal and you go and find the temperature at which it boils, right? If you're asked for the normal freezing point, go to where your pressure is normal, go to the solid liquid line and go down there, all right? So these are your normal freezing points. So I'll write the word normal right there. And it's normal because the pressure is normal, it's standard. And this would be your normal boiling point because once again, that pressure is standard, it's normal. All right, let's stop right there.